Good morning, all of you. Good morning.
Good morning, sir.
I hope I am audible.
Good morning, sir.
Good morning.
Yes, sir.
Okay, let me share my screen. Okay. I hope the screen is visible.
Yes, sir.
Okay. So we will start with our next topic, which is folding. This is your chapter 6 of your KK Parhi. Okay. So chapter 6 you can refer for whatever we have discussed. Till now we have completed our second, third, fourth, fifth chapter. First chapter was just an introduction. So second, third, fourth, fifth chapter that we have completed, and today we are starting from the sixth chapter. Okay. I believe that I am writing something with and it is also visible with red line. Yes.
Yes, sir.
I hope it is visible. 1 minute. Okay. So now we will start with the folding. Now till now, whatever the techniques that we have seen, they are mainly talking about the optimization in terms of the speed. That means if we want a performance, then probably you can apply retiming, you can apply pipelining, parallel processing, or even we have seen the unfolding. Okay. So all these technique are basically useful when you want to optimize in terms of the speed. Now today we will start with the technique which is called as a folding, which help us to do the optimization in terms of the area. Okay, so this is the first of the means technique that we will use it for the area optimization. Now if you want to go for area optimization, then you need to go for a folding. Now what is the concept of the folding? So that we will see first. Okay, now ultimately with the help of the folding you can use the register minimization. That means if in a particular architecture, if your number of registers are going to be reduced, then ultimately your area is going to be reduced, as well as if you want to reduce your functional unit. Okay, so then also the folding technique will be useful, so that we will see. Now ultimately always we in this subject we used to talk about the DSP algorithm. Okay, so in a DSP algorithm, when you want to apply area optimization, then folding would be very useful. Now what folding will be doing? So folding is able to use a single functional unit or maybe some sort of limited number of the functional unit in a time multiplex form. So what I mean by time multiplex form, that this particular functional unit would be used by multiple times, okay, over a period of time in order to complete the functionality. So if I want to do, let's say, a 4-bit addition, then probably I can do one approach is where I can have a 4 adder, I can apply all 4 input and I can generate the output. That is the one way. Another way of doing that is I will use a single adder, but I will apply all the input one by one, which is something similar to what we discussed as a bit serial architecture in unfolding. In my last class, we have discussed about the bit serial architecture. If you remember that one example where we are applying a 4-bit input A0, B0, then A1, B1, A2, B2, A3, B3. So those input are being applied one bit at a time, and with that you are generating your output. So ultimately folding is applied in a DSP architecture that can be operated in a single or a multiple clock cycle. Okay, so similar kind of functionality you can apply it in a single clock cycle or a multiple clock cycle. It depends upon your functionality. So it helps to reduce the number of hardware functional block. Okay, so ultimately we want to reduce your number of functional block in order to reduce our area. Okay, so for that the folding is being used. Now folding is being identified by a folding factor, which is we used to define as a n. Now in last chapter when we talk about the unfolding, then unfolding factor is being defined by j, while the folding factor is being defined by n. Now this notation is I am following from your KK Parhi. Okay, so we are considering a KK Parhi as our reference book. Over there, this notation they have provided where they have considered a folding factor as a n. So you want to reduce your number of functional unit by n number of times. Okay, at the expense of increasing the computational time by factor of n. So always there is a trade-off. Here we are talking about the area optimization. So area we are optimizing with the trading of my speed. Okay. So with the reducing the area, the speed would be suffering. So like example in a bit serial architecture. Bit serial architecture is nothing but your folding. I think somebody has mic on. Please. Hello.
लग्जरी कैंटीन
Hello.
लग्जरी कैंटीन नहीं हो रही है
Anjali. Okay. So what we were discussing that if we want to reduce our functional unit by count n, then at the same time our computational time will be increasing n number of times. Okay, like what we discussed in a bit serial architecture, that if we want to do a 4-bit addition with a single adder, then ultimately I require a 4 clock cycle. Okay, because I want 4-bit addition. At each clock cycle, 1 bit is being added. But if I have 4 adder, then I can complete in a 1 clock cycle the addition of my 4-bit. So that is a trade-off that you need to consider. So ultimately folding will lead to an architecture that uses large number of register, thus present the register minimization technique. So that we will see that if we want to reduce the area, then of course we need to also think about how we can reduce the minimization of register. Okay, because now probably you are using a time multiplex form where a single resource or single functional unit, you need to execute it multiple times. So in order to execute it multiple times, that we consider as a somewhat a sequential in nature. So in a sequential in nature, you need to actually store the value. Okay, so that storage is nothing but it is in terms of the register. So that register also you need to minimize. Okay, so ideally if you want to improve your area, then if you reduce the functional unit but against which the equal amount of register is being used, then there is nothing optimization that you can get. Okay, so ultimately by reducing the functional unit, the optimum way, the number of register also that you need to decide for your functionality, and register minimization techniques is also equally important. So in a folding, we will see how we can reduce the functional unit, and then we will see how we can reduce the number of registers. So there are some techniques are available through which you can do it. So just to explain the basic concept of the folding, the one simple example is given where you just observe that on the left hand side, this particular circuit is one particular DSP block where you want to add three values. So that AN is being added to a BN. So here AN plus BN will be generated. It will be added to the CN. So your YN is nothing but AN plus BN plus CN. Okay. So this is my functionality that I want to achieve. Now here if you observe that, then ultimately if you look at this, then over here the two adder is being used. So 1 and 2 adder is being used. If I am consider the time is TA. Okay, then ultimately maybe if you want to optimize in terms of the speed, then maybe you can think about putting a buffer over here so that you can execute in a only a time duration of TA. Okay, so important thing is we are talking about the area optimization over here. So here we have a two adder. Okay, so that means two functional unit which are in terms of the addition functionality. So that we want to reduce. So how we can reduce it? So of course we want to do addition. So we ultimately we want AN plus BN. Okay, so that is being added with the CN. So now what we can do that in first instance we can do addition of AN plus BN, where this will be added in a second time with CN in order to generate the overall output. So here instead of using two adder, let's consider as a B part which is on the right hand side a single adder. Okay, I am using a single adder, but ultimately in order to generate this particular YN, I need to do the addition two number of times, AN plus BN. So that means this particular adder which we are talking about, this has to be utilized two number of times so that we can get the functionality of YN, which is AN plus BN with addition of CN. So that's why we will use a folding factor N over here as a 2. Okay, so here we are folding our architecture by a factor 2. What I mean by folding factor, because this particular functional unit which we define as a adder, it has to be utilized two number of times in order to get this particular functionality. So that's why here 2 is being considered. So this is in general NL plus U. N is a folding factor, L is just to define a loop, and U is an instance. Okay, so there are two instances, 2L plus 0 and 2L plus 1. So as this loop run two number of time. So in a first instance is I am identifying 2L plus 0, and second instance I am identifying 2L plus 1. Okay. Now in order to use these two instance, I am using a switching kind of activity. So switching will identify that at which particular time a particular switch is being closed. So at the first instance and second instance is being defined by a switching. So here for a adder, so ultimately adder require two input. Okay. So there will be one input from here. Let me just erase it. One minute. Okay. So what we were discussing that ultimately here there is a switching. Now through this particular switching, you will observe that through this particular switching, two instances are being connected. Now for a adder, two input are there. First input is coming at this particular point. Second input is coming at this particular point. So in a first, what we want to do first, we want to add an with bn. Okay, so here there will be an, here there will be n, here there will be cn, and there will be loop kind of structure. So when I define 12 plus 0, so that means switch at this particular position. So when I apply an at that time, I need to apply bn, so that means switch will be in this position. Okay, so when I consider a first instance, then 12 plus 0 will be considered. So for a adder, first input is coming from this end and second input will be coming from this end. So this way an plus bn will be added. Now whatever the output is there, that will be stored. Now I need to add cn, but that cn has to be added in a next instance. So every instance will define a one clock cycle. So this is my first clock and this is my second clock. So in a first clock cycle, first instance will be executed. In a second clock cycle, second instance will be executed. So when the first instance is being executed, you will like to store it into a D flip-flop to ensure that whatever the output of the D flip-flop that is available for my second clock at this particular second instance. So that 12 plus 1, when 12 plus 1, that is the second instance will be executed, then output from this particular D flip-flop. What is the output? The output is an plus bn, which is being stored over here. That will be applied at 12 plus 1 instance. At the same time, the switch, when the switch is in this position, when 12 plus 1 instance is there, then this particular position of the switch for my second input. So that means Cn will be added to a n plus bn and the output will be generated. So when next time the 12 plus 0, so what will be the sequence? So sequence will be like this. See, for a first clock cycle for this particular circuit. Now again I am just removing it to just, oh sorry. Okay, now for a 12 plus 0 and for a 12 plus 1. Now what happens that initially, okay, what I will do, or maybe you can consider that is my first instant, that is my second instant. So that is my first set of input, that is, or even I can define as a clock. This is my first clock, this is my third clock. So that is nothing but my cycle. But here it is starting from 0 because I am initializing. For initializing, they are considering clock as equal to 0. So where the first instance is being executed. So that means switch connection is over here and over here. So at that time, A0 and B0 will be added. I am considering first n is equal to 0. So A0 and B0 will be added and then it will be stored it over here. So here the output of A0 and B0 addition will be stored. So that output will be available in a next clock. So that means clock cycle 1 when it is being executed. So at that time the switch will be in this particular position. So let me show with the another color. So this is the position of the switch at this particular instance, as well as at this particular instant the switch position is like this. So here an plus 0 b0 which is being stored over here, that is applied as a first input of the adder, and the second instance when I consider n is equal to 0, that C0 will be applied. So in a clock cycle 1, where the second instance is being executed, over there A0 plus B0 will be added with C0. Now in a next clock cycle, that means the second cycle, or by number if you consider, then it is a third one. Okay, so third clock. So at that, again my n is equal to 1 will be applied. Now next set of input will be applied. So A1 and B1, again it will be added A1 plus B1, which will be stored over here, and at the same time the switch will be in this position and C1 will be generated. Okay, so when A1 and B1 will be applied over here, 12 plus 0. So at that time, whatever the output which is being generated in a previous clock cycle, that is A1 plus A0 plus B0 plus C0, that is the output of 12 plus 1 instant, that will be stored over here, and that will be latched at Y of 0. Okay. So at first, when you are starting at 12 plus 0, there is nothing will be stored over here. So if you just close this switch, when A0 and B0 is applied, at that time, nothing is stored in a D flip-flop. So there is no output over here. But when the second time 12 plus 0 instance is being executed, so at that time, the value which is being stored over here, A0 plus B0 plus C0, at the end of the second clock, that will be available as a Y0 over here. And at the same time, when the value is being stored at Y0, the next set of input for n is equal to 1, that is A of 1 and B of 1, you can apply. Okay, so that could be done. So this D flip-flop is there. So D flip-flop is just to ensure the pipeline stage. So this, the left hand side of this D flip-flop will be executed at the same time. The right hand side of the D flip-flop will be executed. So right hand side is nothing but generation of Y0, and left hand side is nothing but addition of my A1 plus B1. So A1 plus B1 again generated in a next instance. This C1 will be added and generate this output. So this way the output will be generated as Y0, Y1, Y2 after a 2 clock cycle. So this particular operation, whatever is being defined in this would be completed in a 2 clock cycle, because here what we are doing, we are folding by a factor 2. Okay, so this particular adder will be executed 2 number of times. So as we are reducing the area, the trading is speed. That means computational time now increase the 2 number of times. So that's why whatever the Y0 which is generated previously in a 1 clock cycle, now it could be generated in a 2 clock cycle. So Y0 will be generated at 2, then at 4 your Y1 will be generated. Similarly, your Y2 will be generated at 6, like that. Okay, so this way the output generation is possible. I hope you are getting this concept. If you have any issue, let me know. Is it required to explain it again? This is just to give you a concept of what I mean by folding. So folding is nothing but reusing of a functional unit multiple times. Now, practically, when you want to implement it, then you need to decide that how many resources that you have. Maybe if I have a 1 adder, then probably I need to use a folding only in order to get this kind of functionality. But if I have a 2 adder, then probably I can do it. So ultimately in a folding, we are worrying about area as well. Okay, but somehow area we are looking after at least priority. Okay, so usually we don't think much about the area because of the Moore's law. Anyhow, whatever we are getting in a particular area today, after 1.5 year, we will get the twice number of the functionality. But still, in some of the application, you want to reduce the area. Like means our mobile phone. Usually, we want a mobile phone is very user friendly. That means it should be actually in it should be available at my palm size. Okay, not more than that. If the mobile phone is like a laptop, then probably nobody will try to use that mobile phone. Okay, so what we want, that area is also somewhat important, so that it can be very easy to carry and it should be portable. So at that time the area optimization is required. At that time you can think about the folding. Okay, so I believe that this one is clear. Now let's understand how we can apply the folding transformation. Okay, so next thing that we will see, that how we can apply the folding transformation. So this you need to understand, because whenever we want to solve the example for the folding transformation, at that time this concept you need to apply. So folding transformation is a systematic techniques for designing a control circuit for a hardware where several algorithm operation are multiplexed on a single functional unit. Okay, so what you want to do, that the single functional unit should be capable enough to do the multiple thing. Please wait a while, I need to connect the charger. 1 minute. Okay, so what I was discussing. So I was discussing that what is the folding transformation? Folding transformation is a systematic technique where through some designing, clever designing, your hardware minimization is achieved in a time multiplex manner. Time multiplex, why it is required time multiplexing? So usually means time multiplexing, that means a single resource has to be used a multiple time. So at what particular time this particular resource is being accessed, so that I mean by time multiplex. So time multiplexing manner we need to use. Now consider a case where you have a u and v as a operating node. So let's consider u is a one functional unit, v is a one functional unit. Okay, so two nodes are there of my original DFG. Now, apart from that, HU and HV nodes of your folded architecture. So ultimately, when I go for a folded architecture, then this will be transformed to HU and HV. So when I apply a folding concept, then this, after applying the folding concept, this U I am denoting is HU, and similarly this V is I am denoting as HV. Okay, so HU and all HV nodes of the folded DFG. U and V, these two are for your original DFG, and this HU and HV are the nodes of my folded DFG. Now Wx is the x iteration of node W. Okay, so if a one particular functional unit, okay, or one functional unit is nothing but a node in my DFG. So in a DFG, what I mean by a functional unit, that is equivalent to your node. Node is having a delay, and that delay is associated with the functional unit. So node is nothing but my functional unit. Then there is a edge. So maybe U and V is connected like this. Okay. So what is the meaning of the edge? Once the U is being executed, the execution of the V has been started. Okay. So U and V is related by this. So what is the meaning of this? The execution of V depends upon the when the execution of U is being completed, because the output of U is being applied as an input to V. So the execution of U, the executional time of U is very important, because that defines that when the V would start the execution. WE is a delay. So of course this is having a some weight. This age what we are defining, that is having a some weight. So weight always we define in terms of the number of delay element. So this could be D, this could be 2D, this could be 3D, like that. Okay. So the number of delay element, and the folding factor is being defined by n. So as I already informed that this is the notation that KK Parhi is following. So folding factor is being defined as a n. Hash is a number of operations that can be shared by one functional unit. So that means one functional unit is now doing a multiple thing. Like in our previous example, that we want to do the addition two number of times, but we have a one adder only. So that adder will do both the addition in a time multiplex manner. That is 12 plus 0 instance and 12 plus 1 instance. Now folding set. So this concept we will discuss, but what is meaning by folding set? The folding set defined that order of the operation that will be executed by a functional unit. Now the functional unit is doing a multiple thing. Okay, that means it is doing a multiple operation. But which operation it has to perform first, which operation it has to perform second. So that order has to be defined. So that is nothing but my order set. Okay, so order set, or you can consider a folding set, that defines that in which particular order a operation of this functional unit is being executed. The position of an operation in a U of a folding set is actually a folding order. Okay, so it is ultimately defined in a some sort of this kind of curly bracket, where you will define that, let's say 0, 1, 2, 3. So this is a one order. So that means first the 0 node will be executed, then the first node, then the second node, then the third node. So in this curly bracket, whatever the order is being defined, that is the order that you need to follow for that functional unit execution. So that we will see with the example. So folding set are typically obtained from a scheduling and allocation algorithm. So there are various scheduling and allocation algorithm. Now many of you have gone through the in a last semester the CAD DS subject, the CAD algorithm for digital synthesis. Okay, over there is a specific algorithm for a scheduling as well as a allocation. Okay, so that is applicable whenever you want to do a time multiplexing, then that way you need to apply. Okay, so Miscellany book probably you have followed. So that Miscellany book, the chapter maybe 5 and 6 are there, where the scheduling and allocation is defined. Okay, so that concept that we will apply when we apply a folding concept. Now apart from that, as we have talked about, that there is a node U and there is a node V, and they are, let's consider that they are being connected like this A, and the delay or weight of this particular edge we are defining as a W. Now here the relation is where U executed, then after that the output of U after a delay of WE is applied to V, and then the execution of V has been started. So now the execution of V is totally depend upon when the execution of U is being completed, because once the execution of U is being completed, it will generate the output, then that output is applied as an input to V with the delay of WE. Then the V execution would be started. So that means the execution of V is totally depend upon this WE value and as well as execution of U. Now this execution of U also depends on how the internal pipelining of U is being applied. Okay, so this U is one particular functional unit. This U could be pipelined also. So when I say P of U, then P of U is the number of pipeline stages that is available in my HU. See, when I consider U and V and when I apply HU and HV, then HU and HV is a ultimately after applying the folding concept, if I want to represent a U, then it will define as a HU and then V is being defined as a HV. Now, this HU and HV is having also same relation that once the HU is being completed, then and then HV will be executed. But now we need to know about the pipeline stage of HU. Now, why it is required? Why the pipeline stage of HU is required? If you remember the pipeline stage, if you remember that once we discuss about this way, the pipeline stage, that if I have a 3 pipeline stage for a one particular functionality, then number of pipeline stage is actually defined the number of clock cycle delay. Okay, if you remember our third chapter where we will discuss about the parallel processing and pipelining. So if I apply input over here and output which is generated at this particular end. So once I apply the input, then here there are the pipeline stage. So if I consider this is a 3-stage pipelining, that means 2 buffers are there. So this is my first stage, this is my second stage, this is my third stage. So in a pipelining, every clock cycle, each and individual stage is working. So initially when I define that, then this stage is working. Then when the output is being applied to this second stage, then I can apply the new input. When the third stage is working, at that time second stage is working and first stage is also working. Okay, for my next input. So this way the pipeline stages of a node U is very important. If this particular node is having a 3 pipeline stages, then what is defining that the 3 clock cycle delay will be there to complete the execution of U. Now why we are worrying about execution of U? Because the V execution is totally depend upon the execution of U. So now the execution of U depends upon the number of pipeline stage that it is having. So that's why the P of U, that means the number of pipeline stage of U is very important, because the number of pipeline stage of U defines how much time the U will take to complete the execution. If the U has a 3 pipeline stage, then of course the 3 clock cycle delay will be over here. Plus this WE, then and then we can start the execution. So that's why the PU, the figure which suggests that pipeline stages of U is very important for us. If PU is 0, then HU is not pipeline. So that means there is no pipeline inside U. So if I consider PU is 0, then that means there is no pipeline. But if I consider PU is equal to 1 or PU is equal to 2, then that suggests that this is a 1-stage pipeline, this is a 2-stage pipeline, this is a 3-stage pipeline. Okay, so PU decides the number of clock cycle delay that you can have. Plus this WE is very important. This WE is decided that after how much time the input of V is applicable. Because once the input of V is applicable, then and then I can start the execution of V. So what will be my folding equation? The folding equation from DFU to V is this one. Now this you need to understand with this particular circuit. Now the relation is from U to V. Now let me rub it and then okay. Now if you want to understand this equation U to V, then you need to understand ultimately this concept. Here I have a U. Here I have a V. And U to V there is a connection. So that is the meaning of this. Okay. So U to V there is a edge. Now, if I am considering U to V, then I need to consider when the U will be executed and when the V will be executed. So always when we want to apply, then D of U to V, then this is for destination and this is for your source. Now if you remember the retiming, in a retiming also we are applying R of U minus R of V minus R of U. Okay, so that means we are first thinking about the destination node, then we are thinking about the source node, and that we are subtracting. So ultimately source node is being subtracted from your destination node, and that way we are considering the overall time. So similarly in a folded equation is also like that. We need to think about this V is our destination and this is our source. So when the source will be executing and when the destination is will executing. Now this U and V are my folded architecture node. Okay. So that means this V could be executed multiple times and this U could be also executed multiple times. Okay. Or for that I am defining the instance as NL plus V, and here the instance is NL plus U. Okay, so NL plus U and NL plus V, I am defining the instance which is being associated with my source node and destination node. Source node is U, so for that I am considering the instance NL plus U. What this NL plus U suggests that this is in a folding form, because this particular resource or this particular node or this particular functional unit is executing multiple times. Okay, that I mean by applying a folding. Okay, so as we want to apply a folding, so U and V will be executed multiple times. So they are doing a many more operation, and that number of operation they are completing in a number of clock cycle, and that I am defining as a NL. So N is I am considering as a folding factor, L suggests the loop, and NL plus U suggests the particular folding instance. So this U could be 0, 1, 2 like this. That depends upon N. So U usually goes from 0 to N minus 1. So if my N is 4, then the U could be up to 3. So that is 4L plus 0, 4L plus 1, 4L plus 2, 4L plus 3. 4L plus 4 is nothing but the execution of the same thing. Okay. So U could be 0, 1, 2 up to N minus 1. Similarly, that is applicable to V also. So V could be 0, 1 up to N minus 1. Now, in general, if we want to understand that this U is being executed and V is being executed, now we need to find out when the U will be executed. So ultimately, we need to consider destination minus source. So this is the destination, this is the source. Now, first try to understand the delay of this particular source. So NL plus U is the instance at which the U will be executed. All of you will agree. Okay, so NL plus U is nothing but the instant at which the U will be executed. Apart from that, U could be having an internal pipelining. So that many of the clock cycle it will take. So here NL plus U plus this P of U. Why P of U? Because we should know that how many pipeline stage we have at U, because U is a source node and the destination node execution is totally depend upon when execution plus here the delay of this particular execution. So this two is very important in order to know the execution of V. But first of all, we need to understand that when the execution of U is being completed. So execution of U could be completed at NL plus U instance plus this U. If it is a pipeline, then we need to add that delay. So PU is always an integer. Just we talk about that PU could be 0, it could be 1 or it could be 1. So here we only talk about that PU could be 0, 1 or PU could be 2. So that we need to add it over here. 0 that means there is no pipeline stage. 1 that means 1 pipeline stage. 2 means there is 2 pipeline stage. So here always the PU need to execute because that defines that when the U will be completed its execution. So NL plus U plus PU is very important. So once the NL plus U plus PU will be known to you, then you need to add WE. Then you need to identify the delay, or then you can identify that when the destination node will be executed. So ultimately for every loop, N L plus V, L plus WE. Now what is why WE we are adding? Because this V, execution of V depends upon when the U is being completed, plus every time this WE delay will be added, and then V will be starting his execution. So that's why here N L plus WE, this is very important that you need to understand. So for every time when U is being executed, then WE delay will be added and then we will be starting the execution. So that's why here N L plus W, and that V is the instance at which the V is starting the execution. So for a destination node V, N L plus WE plus V minus for a source node N plus U plus PU. Now there is no need to know about PV because we don't require. Why PV is not required? PV stands for pipeline stage of V, because we are not at all worried about the pipeline stage of V, because V is a terminal point. At this the activity ends. Okay, if you have a connection like this, where V is being connected to U, so at that time we should know P of V, because here this now act as a source node and this act as a destination node. But when we are considering that U2V activity, then this U is a source node and this V is a destination node. So that's why there is no way that PV will come into this particular equation. But of course, PU is important because I should know that when the source is completing its execution. Now in order to know the time for the source node completion, I should know the PU of U. That means how a pipelining is being applied to my source node. So that's why PU is there. There is no PV for this particular equation. And this way, this will be your final equation that you will apply for a folding transformation. Okay. So whenever you are getting any negative value in the folding, then you need to apply the actually retiming to make it positive. So that we will see. Okay. So negative value of the folding equation. It may happen that by putting this value N, W, PU, V and U, you are getting a negative value. Okay. But we know that the delay element cannot be a negative. So we need to make it positive. Okay. So for that you need to priorly apply a retiming. You need to ensure that this value is positive and then you need to apply the folding. So that would be more clear when we will discuss the example. So at the time of the example we will discuss this in more details. Okay, but here there may be a case where you need to apply a retiming, and retiming you need to apply whenever you are getting your delay element value as a negative through this equation. So at that time you need to apply the retiming. Okay, so for today probably we are ending at this particular point. Okay, so this will be your final folding concept, where HU is a folded node, PU is the number of pipeline stage, so that many number of delay element that you need to consider, and then D of U to V, that means U is being connected to V, and that instance is NL plus V for the execution of HV. Okay, so this equation you need to understand. So this equation we will use when we will solve the folding problem. Okay, so how this equation is being derived, so that I have explained with this particular concept. So maybe you just try to read this, and if you have any problem, let me know. Now, if whatever I have explained today, if you are having any issue, let me know. We can discuss. Otherwise, you can refer a chapter 6 of KK Parhi, where the folding transformation is explained. So initially 3-4 pages of the KK Parhi of the chapter 6 I have covered today. So tomorrow when we will meet, we will discuss about the more about the folding when we will talk about the register minimization technique. Yes. Any doubt whatever we have discussed today? Maybe I can see in the chat box. Okay, it seems that there is no doubt. And if there is a no doubt, then we can end up our session today. See you next time. Thank you.
हेलो
हाँ, yes.
सर प्रीवियस क्लास के साथ स्लाइड शेयर कर दीजिएगा.
Okay, मैं कर दूंगा. ठीक है.
ओके सर.
Anyhow, actually, I am using the slide directly from one of the author. So from this particular website, you can actually download the PPT, whatever I am covering. But anyhow, I will share it with the
Canvas.
with your canvas. Okay, no issue.
ओके सर.
Okay. Thank you all of you. See you next time. Bye. Have a nice day.